Hello, everyone. My name is Aaron, and I'm a research assistant and a student at the Intelligence System Research Institute at Sungkyunkwan Kwan University. I'm here to introduce a project that we are currently trying to solve. This is the 3D beam packing problem. This work is supported by Hyundai Motor Company. Here we have a diagram describing the 3D beam packing problem. The problem consists of packing items of variable size into a bin or pallet with the idea of maximizing the space utilization. There are multiple variants of this problem. In our work, we focus on a more realistic setup where we have to respect the sequence of the items delivered with the exception of a small buffer. In some cases, the items can be reoriented to improve performance. For simplicity, both the bin and the items are discretized as is depicted in the right figure. In this slide, we summarize some of the typical solutions to tackle the problem. First, the most basic brute force algorithm. Although they assure optimality, it is not practical as the problem has a huge search space. The 3D beam problem, is defined as a strongly NP-hard problem. Another alternative is to use heuristic models. Although optimality cannot be guaranteed, they can enormously reduce the computation. They have been extensively utilized for solving the 1D and 2D versions of the beam packing problem. Finally, reinforcement learning algorithms have shown superhuman performance in many games or environments, yet they have not been widely applied to the beam packing problem. In our work, we focus on the deep reinforcement learning approach to learn the optimal packing. Reinforcement learning is primarily defined by two entities, the agent and the environment. The agent takes actions changing the state of the environment at each time step. The environment, in addition, provides the agent with the reward signal. The main objective of the agent is to find the optimal behavior to maximize the notion of the accumulated reward. More particularly to our problem, the state is defined by two qualities, the bin status and the next items to be packed. The bin status is defined by the height map of the bin. The action, on the other hand, is the location where the next item will be placed. Also, to avoid instabilities, the action mask is defined in order to remove the locations that are invisible. We developed the environment with a game engine called Unity 3D. It provides with great capabilities and a physics engine which allows simulating a real environment. The environment also renders nice 3D visualizations of the packing process. Furthermore, we add a panel to allow human interaction, as you can see on the left side of the software, so that we can also test the human performance in the 3D beam packing. The agent behavior is defined by a deep neural network. Typically, the state is at the input, and we can either predict the action probabilities or the value, the accumulated future reward. There are multiple algorithms to train the neural network. Some of them assumes that the dynamics of the environment are known, also known as model-free methods. Another assumes that the dynamics are given or can be learned, model-based in this case. The figure on the bottom right shows some examples of algorithms in their respective categories. In our experiments, we suppose bin is 10 by 10 by 10 cuboid, and we use an item data set with items between the size 2 and 5. In this experiment, we assume that the buffer size is 1 and no reorientation is allowed. To measure the performance, we compute the average space utilization and the average number of packet items across multiple episodes. As you may see in the table, a random policy only obtains 30% of packing, PPO, a popular algorithm, obtains up to 60%. And in our work, we actually obtain the highest performance with 83.4% of this utilization space. And here we have a short clip depicting the training process of the agent with the Unity 3D environment. And that was it for the presentation. Thank you for listening, and thank you for your interest in our laboratory.